Then you're doing exceptionally well. Oh, goodness gracious, we're not wanting to rotate. Okay, let's get this started so we can get this done. Chapter 7, 1 plus 1. 1 plus 1. We are down to our last 4 chapters together. Just saying. We got a little bit of work to do before we get to the end. But I'm going to start peppering the weeks with like exam review classes. Okay? I know you're super excited. So keep that purple exam review with you. Okay, exponential functions. Super fun. So an exponential function is given where a is the constant or rational number, and x is the exponent. So a has to be greater than 0. So it's saying it can be a rational number instead of constant. So we will when we do transformations, but for right now, your base number is going to be our positive rational number. And I say rational because it could be a decimal. Okay. All right, so easy peasy, we have an exponential function. So, David, we're going to do table of values. The David of values. So, if I put in my standard -2, -1, 0, 1, 2, that's my standard issue axis, what's happening with the y's? So if you put in -2 as the exponent, so 2 to the -2, do we remember what negative exponents do? Reciprocate it, they flip it. So this is the same as saying 1 over 2 to the exponent 2. So what's that? Oh, on 4. You're brilliant. So 2 to the exponent -1. 1 over 2. Oh, my PC just disconnected for some reason. We'll see if there's actually audio to this. Okay, so 2 to the exponent 0. 1. Anything to the exponent 0 is 1. 2 to the exponent 1 is 2, and this will be 4. Pretty easy. So if we were to plot this, so this would be 1, 2, 3, 4, 5. 1, 2, 3, 5, and we'll do 5s and 5s. So -2, I'm at a quarter. -1, I'm at a half. At 0, I'm at 1. At 1, I'm at 2. At 2, I'm at 4. So these should be connected with a curve. Now, does the graph continue? I hope so too. Will it cross the x-axis here? The answer is no. How come? It's never going to turn negative. A negative exponent is never going to turn your actual power negative. It will make it really, really small. Like if I have 2 to the exponent -10, that's going to be 1 over 2 to the power of 10. What's 2 to the power of 10? I'm just going to do it in their calculator. Well, how much is it? 1024. And if we put that into a decimal, it's just becoming a really, really small number. So this, it's almost like that x-axis has asymptotic behavior. You guys know what I mean by it? It's not an asymptote, but it has asymptotic behavior. So it heads towards the x-axis. It gets really, really close, but it never crosses. Okay? It wants to be an asymptote. We refer to this as an increasing function because as the x increases, what's happening to the y? As x gets bigger, what's happening to the y? Y is getting bigger too. So as x increases, y increases, that's considered an increasing function. All right, so a derivative of values again. It is what it is, David. That's what you do. So I'm going to go -2, -1, 0, 1, 2. My x's are staying the same. Now my y's. So I want to point out something to you that's going to cost you a half mark deduction. My base number is 1/2. That must be inside of brackets. Okay? Because if you don't, then that means that exponent only applies to the numerator. And that would be incorrect. So if you are doing a fraction as a base number, it has to be inside brackets. So just keep that in mind. So if I have 1/2 to the exponent -2. I don't know what's happening with my marker. We're just going to hope you guys are writing better notes than I am today. So what does the negative tell me to do? Reciprocal, so we're going to flip it. So 1/2 becomes 2. 2 squared is 1, what's that going to be? 2. What's 0 going to be? 1. To the 1/2 to the exponent of 1? 1/2. That's what you meant. 1/2 to the exponent of 2? 1/4. Okay, so at -2, I'm at a +4. At -1, I'm at 2. At 0, I'm at 1. At 1, I'm at 1/2. And at 2, will it cross the x-axis? No, because it has asymptotic behavior. And we would call this a decreasing function. A decreasing function because as x increases, so as x is increasing here, what's happening to the y's? They're decreasing. So our y's are decreasing. So we call that a decreasing function. Easy peasy, right? Awesome. Table of values for this one. So -2, -1, 0, 1, 2. What is the exponent of -2? What is the exponent of -1? 1, 1, 1. Almost like it's a straight line. Is that an increasing function? Is that a decreasing function? What is that called? It's a constant function. Because that's all you're getting here. You're just getting that same repeating constant. We call that a constant function. So why is that changing? They are just a number. So it's a constant function. So think the alarm, did you see that? Will that occur anywhere else? What about -1? No, because -1 would flip back and forth between +1 and -1. -1 squared is +1, but -1 cubed is a -1. It does. It's weird. It would go up and down. Yeah. It's almost, but they would be sharp lines. They wouldn't be the smooth curves. So this doesn't occur anywhere else but at +1, but keep that in mind. Okay, characteristics of exponential functions. Let's say not be above 3. We'll say first 2. The first 2 examples. So your 2 to the exponent x and your 1/2 to the exponent x. What's the domain on those? What's your range? Inclusive or not inclusive? Not inclusive. That's weird. We usually don't have that, right? But it's that asymptotic behavior. What's the common point? The common invariant point. 0 and 1. Okay, so if A is greater than 1, so if A is greater than 1, that's with the first example. What kind of graph do we get? It's increasing function. So we're going to get a graph that goes like that. And if A is that fraction between 0 and 1, it's going to be decreasing, yeah. Just like fill in the blank notes. Remember when that was like a big thing in elementary? And if A is equal to 1, what do we call that? Constant function. Yeah. Yeah. Yeah, absolutely. All he's saying is, so I go back to this, he's saying, look at these three. If your exponent is 1, it's whatever the base is. If your exponent is -1, it's going to be the reciprocal of the base. And if you have an exponent of 0, we know it's going to be 1. That's all Kevin was saying. But we know that's for negative values, so it's not. I give up. Okay, what are we supposed to do here? Oh, constant function, this results in a horizontal line. Did you? Oh, comments required. Okay, so now we need to create an equation. You guys ready?
Yes.
I love it. No. Okay, look at this graph, increasing or decreasing. So what do you know about the base number? It's a fraction, right? Okay, what do you know about what Kevin said? It's a thing. So when we go back to our negative values, if we have an exponent of 1, the graph is equivalent to the function. So what are we going to look for here? So we identified that it's decreasing. We identified that it's decreasing. So we know we've got a fraction base. That's what that tells us. And we now have to find when x is equal to 1, because whatever the function is, whatever the y value is of that, that's your base. When x is equal to 1, y equals your base number. Does that make sense, everybody? Because your exponent's 1, and use base 1 is itself. So what do we know about this graph? Okay, hold on. It doesn't give us the point at 1. Now, I don't know about you guys, but it's definitely hard to read. So what I can do is, so this didn't work, sad face. So when x is equal to -1, y is equal to 1 over the base number. And that point is listed. It's 4. So what would be the equation for this graph? Y equals 1 over 4. In brackets, to the exponent, x. No, a is your base number. Oh, does it say that? I thought it said CX. Can we just call it X? Are we down with calling it X? Does that make sense for you guys? So this one works for this graph. Obviously, I'm always going to go here because it's like, I don't have to worry about doing any mathy stuff. It is just the base number, but I couldn't see it. Couldn't see it. So the -1 is just the reciprocal of whatever the function is. All right. Okay, so this is chapter 7 and chapter 8. This is what I said on Friday for those of you who weren't here. Question number 2 or 3 on your exam is some weird wonky formula. A formula that you've never seen before, that we didn't show you. But the understanding is I should be able to use any formula that has something to do with exponents, and you should be able to find it using your exponential knowledge or your logarithm knowledge. So expect that you get a formula that you've never seen before on that provision. It's okay. You have the tools to deal. You just like, it's kind of like saying, okay, I've built dog houses all the way along. Now I need to build like a shed. We're just going to go to a shed. We're going to scale it up a little bit. So you're doing similar stuff, and you can use all your knowledge to build something better. You would use exponential functions when we're looking at, we call it exponential growth, exponential decay. You guys do that in chem? No? No. You don't talk about the decay, the exponential decay of. Okay. Shows up in chem too, but usually decay more than growth. So half-life is how long it's going to take for it to get to half its original mass. So exponential decay is just a decreasing function. And your exponential growth is an increasing function. Wait, so here we got a word problem. Oh, and there's a graph. Perfect, we don't have to graph it. Radioactive sample of radium has a half-life of 15 days. So what does that mean? Of its initial amount, right? 15 days and then you're down to half. Of the mass and ground, so the remaining time t and 15-day intervals can be modeled using this exponential graph. So at day 0, it's at 1. First 15-day interval, it's at 0.5. The second 15-day interval, number the 2 increment is actually 30 days. Does that make sense to everybody? The units of measure are 15-day chunks. So at 2, you're at 30 days. At 3, you're at 45 days. At 4, you're at 60 days. Okay, we know that this is a decreasing graph, so this is exponential decay. What's the initial mass of radium in the sample? So at time 0, where are we starting? We're starting at 1 gram. Okay. Perfect. And then it says, what value does the mass of Ra25 remaining approach as time passes? Where is it getting to? Yeah. So we start here, and we are approaching 0 grams. Will I ever get to it? Will I ever get to 0 grams? No, it's always taking a half of a half of a half of a half of a half. Well, yeah, but we're just talking about it sitting there decaying. Kind of like you guys sitting there not using your brains. Brains decaying. Luckily, that's not the case. What's the domain and range of this function? What's the domain? Let's start with domain. Inclusive or not inclusive? Inclusive. Does that make sense to everybody? Because T0 is when we start. And then the range for this is going to be what? 0 to 1, inclusive of 1, but not inclusive of 0. Good job, guys. Good job. Rate of exponential decay flow that relates the mass of the radium to the remaining time of 15 days. So what it's asking you to do is create an equation. Half-life, what's your base number? Again, if we go over here to our equation, we said if you look for when x is 1, this would give me my base number. So we would have 1/2, my base number. And what else do I need on there? I need an x. And that's going to equal mass remaining. I have to put a condition on x. What does x have to be greater than? 0. Could it be equal to 0? Was x equal to 0 on our chart? Let's go again. Let's look at it. Can I have look at our domain. Does it include 0? Yes. So x has to be greater than or equal to 0. Now there's another formula that you could have done. M equals M initial times 1/2 x. M initial being the original amount that you started with, it was more than 1. Does that make sense to everybody? If I was starting with 200 grams of radium, that is a lot of grams. Estimate how many days it would take for radium to decay to 1/30 of its original mass. We're going to be estimating, folks. Estimating because we don't have logarithms yet. And people say, do I have to do it this way? Once you have the knowledge of logarithms, you can solve for log, like using logs, but for the rest of us mere mortals who haven't got there yet. So we know the mass remaining is 1/30. So 1/30 equals 1/2 to the exponent x. So 1/30, do a little bit of math over here, is 0.03 repeating, right? Yeah, you guys believe me? What you're going to have to do is you're going to have to do guessing and checking. I don't like it. There's a way to do it without guessing and checking, but we're baby stepping this. So I know that 1/2 to the exponent 1 is 1/2. I know 1/2 to the exponent 2 is 1/4. I'm still nowhere close. Anybody want to give me a number? Your knowledge of base 2 exponents. Go through them in your head. 2 to the exponent 2 is 4. 2 to the exponent 3 is 8. 16. 32. So if I had 1/2 to the exponent 5, that's 1/32. What's the one that comes before that? 1/2 to the exponent 4 equals 1/16. What do you think is closer? So this one, right? But is it to the exponent 5? No. So we're going to start going, and we know it's greater than 4 but less than 5. So I'm going to start breaking this stuff down. I'm going to go 1.2. This is scary stuff. 4.9. What do I get? Oh, no, I don't have a calculator. Anybody? Three, 4, 9. If I go 1/2 to the exponent 4.8, what do I get? Which one's closer? 4.9 or 4.8? 4.9. Okay, so my x is 4.9. Is that how many days it is? Is that how many days it is? What were my increments on the x-axis? What were they measured in? 15 days. So I've only gone 4.9 intervals. And how much is each interval worth? So we're going to times that by 15. How many days do I get? So we've got 73.5 days. How many people would have remembered to times by the 15? Doing that you would have drawn? I probably would have screwed it up. Kudos to you for remembering. But it's those little things that are going to take you from, it's not that you don't know how to do the math, it's just paying really close attention to the questions that are being asked. I could have another pea break. This is delightful. Under ideal circumstances, certain bacteria population triples every week. This model is an exponential graph. Is it decaying or growing? Growing, so it's an increasing graph. And it triples. Triples. What's my base number? 3. Right? But we can confirm that with the graph. What are the domain and range of this function? So the domain is 0 inclusive to infinity, and the range one inclusive to infinity. We're an exponential growth model. So this is growth model. I'm looking for an equation. So many words. Okay, so find what when x is 1, what's my y value? 3. So what's my base? 3. I think we already talked about that. So we would say the number of bacteria in relation to time is 3 to the exponent t. Well, then I have to put x in here. If you're going to use x in here, you got to put x in here. And what do we know about t? T is my domain. It's a restriction on it. T has to be, because we're not going backwards in time. It says determine approximately how many days it would take for the number of bacteria to increase to 8 times the quantity. It should say initial quantity. Okay, so what's my initial quantity? What's my initial quantity? So what's 8 times that? Woo! That one's hard. Okay, so that would be 8 bacteria equals 3 to the exponent t. Again, if we have logarithm knowledge, we can solve this, but if you don't have logarithm knowledge, you're stuck with guessing and checking. Okay, so with that being said, I'm going to go over here. I know 3 to the exponent 1 is 3. I know 3 to the exponent 2 is 9. Am I closer to 2 or am I closer to 1? 2. So now I'm going to back it up a little bit. So 3 to the exponent, let's do 1.9 because that worked for us last time. I think so. What's 1.8? Which one's closer? 1.9. Okay, so T is 1.9 increments. What are increments measured in? In weeks. Remember, T is time, so it's the x-axis. It's measured in weeks, so we have 1.9 weeks, and it asks for it in days. So increments were in weeks. So if I want to know what it is in days, I'm going to take 1.9 and times that by 7 days, and I should get 13.3 repeating days. Okay, that's chapter 7.